This is the video lecture for section 1.1, the division algorithm. So this first chapter, chapter 1, is called Arithmetic in Z Revisited. In this chapter, we'll examine the properties of the set of integers, which is denoted by Z, and this consists of all the negative integers, so -1, -2, -3, and so on, 0, and the positive integers 1, 2, and 3, and so on. We'll assume the usual properties of addition and multiplication of integers, along with the order relations. So for instance, we assume the commutative laws of addition and multiplication for all integers a and b, a plus b is equal to b plus a, and a times b is equal to b times a. We also assume, for instance, the transitive property of the less than relation. This is just one of the properties of the order relation. For all integers a, b, and c, if a is less than b and b is less than c, then a is less than c. In addition to these properties, we also assume the following result, which is considered an axiom of Z. Being an axiom, we assume it without requiring a proof. And this is called the well-ordering axiom. And it states, let S be a non-empty subset of the set of non-negative integers. Then S has a smallest element. That is, there exists an element n sub 0 in S such that n sub 0 is less than or equal to n for all n in S. So n sub 0 is the smallest element of the set S, which means that it's less than or equal to all other elements n in S. Now, if we visualize the set of non-negative integers laid out on a number line, then it seems intuitively plausible that any non-empty subset must contain an element that lies to the left of all other elements in the set. So it seems reasonable to consider this to be an axiom of the set of integers, a statement that doesn't require a proof. The conclusion of the well-ordering axiom, namely that the set S contains a smallest element, does not hold for the set Z of all integers. For instance, the set Z itself does not have a smallest element. The conclusion also does not hold for the set of non-negative rational numbers, as shown in the following example. So for our example, the set S, which consists of R in Q such that R is greater than 0, so this is the set of rational numbers which are greater than 0, or the set of positive rational numbers. And this is clearly a non-empty subset of the set of non-negative rational numbers, but it does not have a smallest element. And we want to show this. To show this, we can use a proof by contradiction. To prove a result using a proof by contradiction, we start by supposing the result to be proved is false, or equivalently, its negation is true. We then need to derive a contradiction. And once we've derived a contradiction, we can then conclude the original result is true. So for this example, to prove this using a proof by contradiction, we're trying to show that S does not have a smallest element, so we'll suppose that is false. So we'll suppose that S does have a smallest element, R sub 0. We then need to derive a contradiction. So let's consider R is equal to 1/2 R sub 0. So R sub 0 is the smallest element of our set S, and we're going to look at the number R is equal to 1/2 R sub 0. Now since R sub 0 is in S, that means that it's a rational number, it's in Q, and it's positive. R sub 0 is greater than 0. Now that tells us that R will also be a rational number, since it's just 1/2 times a rational. And R is greater than 0 as well, since 1/2 times a positive will also be positive. So R is in Q, and R is greater than 0, so that tells us that R is in S. But R is less than R sub 0, so R is an element of S that is smaller than the smallest element of S. And this is a contradiction. And thus our result is true. S does not have a smallest element. So that tells us that the conclusion of the well-ordering axiom doesn't apply when we're looking at rational numbers. It's a very special property of the set of non-negative integers. Now in elementary school, you learn about division of integers. If we divide one integer into another, we obtain a quotient and remainder. For instance, if we divide 7 into 39, we obtain a quotient of 5 and a remainder of 4. This can be expressed by the equation 39 is equal to 7 times 5 plus 4. The number 7 is called the divisor, and the number 39 the dividend. In general, the dividend will be equal to the divisor times the quotient plus the remainder. Our first theorem, the division algorithm, is a formal statement of this division process. So this is Theorem 1.1, the division algorithm. And what it states is, for any integers a and b with b greater than 0, there exist unique integers q and r such that a is equal to bq plus r and 0 is less than or equal to r is less than b. This can be written in symbolic form as shown. For all a, for all b greater than 0, there exists a q, there exists an r, such that a is equal to bq plus r and 0 is less than or equal to r is less than b. Where the domain for a, q, and r is a set of integers, and the domain for b is a set of positive integers. In the theorem, we are dividing the integer a, called the dividend, by the divisor b. According to the theorem, there exists a quotient q and a remainder r satisfying the two conditions in the theorem. Before proving the result, let's first consider a few simple numerical examples. So, for each of the following pairs of integers, we want to find the quotient and remainder determined by the division algorithm. So first we have a is equal to 31 and b is equal to 7. So the theorem tells us there exist unique integers q and r for which 31 is equal to 7 times q plus r and 0 is less than or equal to r is strictly less than 7. Dividing 7 into 31, we obtain a quotient q is equal to 4 and a remainder r is equal to 3, which satisfy our two conditions. 31 is equal to 7 times 4 plus 3, and 0 is less than or equal to 3 is strictly less than 7. For our second example, let's take a is equal to negative 31 and b is equal to 7. The theorem again tells us that there exist unique integers q and r for which minus 31 is equal to 7 times q plus r, and 0 is less than or equal to r is less than 7. Dividing 7 into negative 31, we obtain a quotient negative 4 with a remainder negative 3. Now these values satisfy our first condition. Negative 31 is equal to 7 times negative 4 plus negative 3. However, the remainder is supposed to be non-negative, so this will not satisfy the second condition. Instead, we need to choose a quotient q is equal to negative 5, and then our remainder r equal 4 will be non-negative. These values will satisfy the two conditions in the theorem. Negative 31 is equal to 7 times negative 5 plus 4, and 0 is less than or equal to 4 is strictly less than 7. For our third example, we'll take a is equal to 54 and b is equal to 9. And the theorem tells us there exist unique integers q and r for which 54 is equal to 9q plus r, and 0 is less than or equal to r is strictly less than 9. Dividing 9 into 54, we obtain a quotient q is equal to 6 and a remainder r is equal to 0, which satisfy our two conditions. So 54 is equal to 9 times 6 plus 0, and 0 is less than or equal to 0, which is strictly less than 9. We next want to prove the division algorithm by applying the well-ordering axiom. The general idea in this, and any proof involving the well-ordering axiom, is to first define a set S, which is a subset of the set of non-negative integers. We then want to show that the set S is non-empty. The well-ordering axiom then implies there exists a least element of the set. We want to then show that the least element is what we're trying to prove exists. This will become a little clearer as we go through the proof. It's a little bit vague at the moment. Now the basic idea in the proof is to view division as repeated subtraction. To find the quotient and remainder when dividing a by b, we subtract the divisor b from a repeatedly until we obtain a difference less than b. The number of subtractions to reach this point is the quotient. and the final difference is the remainder. We'll illustrate this procedure in the following example. So let's determine the quotient and remainder when a equal 38 is divided by b is equal to 7. So we want to subtract the divisor b equals 7 from the dividend a equal 38 repeatedly. So we'll start 38 minus 7 is 31, which we can write as 38 minus 7 times 1. Subtract 7, we obtain 24, which is 38 minus 7 times 2, so that's 2 subtractions. Subtract 7, we obtain 17, which is 38 minus 7 times 3, that's 3 subtractions. Subtract 7, we obtain 10, which is 38 minus 7 times 4, 4 subtractions. And one more, subtract 7, we obtain 3, which is 38 minus 7 times 5. We continue subtracting the divisor 7 until we reach a non-negative number which is less than 7. So in this case we've obtained 3, which is obviously less than 7. This number is the remainder, and the number of multiples of 7 that are subtracted, which in this case is 5, is the quotient. So in this example, our quotient q is 5 and remainder r is 3. In the general case, we subtract the divisor b from the dividend a, resulting in differences a minus b times 1, a minus b times 2, a minus b times 3, and so on. After x subtractions, the difference is a minus bx. We stop when this difference is less than b, but still non-negative. So we stop when this difference is the smallest non-negative integer of this form. And this will be the remainder. So the remainder then will be the smallest element of the set S, consisting of differences a minus bx, where x is an integer, and a minus bx is greater than or equal to 0. Since the remainder will be the smallest element of a subset of the set of non-negative integers, we can use the well-ordering axiom to prove its existence. We're now ready to prove the division algorithm. So we'll start by restating it, and we'll begin the proof. Now the theorem is a universal statement, so we start by specifying the variables a and b. So we'll suppose that a and b are arbitrary integers with b greater than 0. And we then need to show that there exist unique integers q and r such that a is equal to bq plus r and 0 is less than or equal to r is less than b. Now there are two parts to the proof. First, we need to prove existence. That is, we need to prove that there exist integers q and r satisfying the two conditions. Second, we need to prove uniqueness. That is, we need to prove that there is only one integer q and one integer r satisfying the two conditions. So we'll start with the existence proof. As discussed above, we want to consider the set S consisting of the differences a minus bx such that x is an integer and a minus bx is greater than or equal to 0. The smallest element of the set will be the remainder, but we need to prove that the smallest element actually exists. And to show this, we want to apply the well-ordering axiom. In order to apply the well-ordering axiom, we need to show that this set S meets the requirements of the axiom, namely that it's a non-empty subset of the set of non-negative integers. Now, since a, b, and x are all integers, and the elements of S have the form a minus bx, then it's clear that the elements of S are integers. And by the requirement in the set S that a minus bx is greater than or equal to 0, each element of S is a non-negative integer. Therefore, S is a subset of the set of non-negative integers. Now, to show that S is non-empty, we need to show that for some integer x, a minus bx is greater than or equal to 0, so will belong to S. Let's consider the following cases. So case 1, let's suppose that a is greater than or equal to 0. So we want to show that for some integer x, a minus bx is greater than or equal to 0. So in this case, we'll choose x to be 0. Then a minus bx will be a minus b times 0, which is just a, which we're assuming in this case is greater than or equal to 0, which implies that a minus b0 will be an element of S. It will be a non-negative integer. Therefore S is non-empty. For case 2, we'll suppose that a is less than 0. And so again, we want to show that for some integer x, a minus bx is greater than or equal to 0. So in this case, we're going to choose x to be a. Now, since b is a positive integer, then b must be greater than or equal to 1. Then 1 minus b is less than or equal to 0, and since a is strictly negative, then a minus bx, which is a minus ba, since we're choosing x to be a in this case, which is a times 1 minus b, this will be greater than or equal to 0. A is negative, and 1 minus b is less than or equal to 0, so their product will be greater than or equal to 0, which implies that a minus ba is an element of S, and therefore S is non-empty. Since these cases exhaust all possibilities, either a is greater than or equal to 0 or a is less than 0, then this tells us that S is non-empty. The well-ordering axiom then implies that S has a smallest element. Let's call it R. Now, since R is in S, then it must have the form a minus bx of elements of S for some integer x. This means there exists an integer x in, we'll call it q, such that r is equal to a minus bq, which implies that a is equal to bq plus r. So at this point, we've used the well-ordering axiom to prove the existence of an element r, and the existence of an element r tells us that there also exists an element q. So we've now proved the existence of q and r. And our two integers q and r satisfy the first condition in the theorem, namely that a is equal to bq plus r. We still need to show that r satisfies the second condition, namely that 0 is less than or equal to r is strictly less than b. Now, since r is in S, we know that r is greater than or equal to 0. To prove the other inequality, r is strictly less than b, we'll use a proof by contradiction. So again, now for a proof by contradiction, we suppose the result we're trying to prove is false. So we're going to suppose that r is less than b is false, which means that r is greater than or equal to b. We then need to derive a contradiction. Now, since r is greater than or equal to b, then r minus b is greater than or equal to 0. Where r minus b, this will be a minus bq minus b, and we can group the terms with b together, and we'll obtain a minus b times the quantity q plus 1. And now this has the form a minus bx, where x is equal to q plus 1. So this looks like an element of S. It has the form a minus bx of elements of S, where x is an integer. And so this shows that r minus b is a non-negative integer which has the form of elements of S, so belongs to S. However, since b is positive, then r minus b is strictly less than r. But r was the smallest element of S, so this is a contradiction. We have an element r minus b which belongs to the set S, which is smaller than the smallest element r of S. Therefore, r must be less than b, so r satisfies the second condition in the theorem. And this completes the existence part of the proof. We've shown that there exist integers q and r satisfying the two conditions in the theorem. For the second part of the proof, we need to prove uniqueness. That is, there is only one choice of integers q and r which satisfy the two properties in the theorem. To prove this, suppose there are two such choices, q1 and r1, which satisfy the two conditions, a is equal to b q1 plus r1, and 0 is less than or equal to r1 less than b, and q2 and r2, which also satisfy the two conditions. So a is equal to bq2 plus r2, and 0 is less than or equal to r2 less than b. We then need to show that q1 is equal to q2 and r1 is equal to r2. This will tell us that there were not really two choices after all, so that the integers q and r are unique. Now, since a is equal to bq1 plus r1 and a is equal to bq2 plus r2, then these are equal to one another, so bq1 plus r1 is equal to bq2 plus r2. And this can be rewritten as b times the quantity q1 minus q2 is equal to r2 minus r1. Take the r1 to the right side, the bq2 to the left side. Now, since 0 is less than or equal to r1 is strictly less than b, then multiplying by negative 1, we obtain negative b is strictly less than negative r1 is less than or equal to 0. Now, adding this inequality to the other inequality, 0 less than or equal to r2 less than b, we obtain negative b is strictly less than r2 minus r1 is strictly less than b. Now, substituting r2 minus r1 equal b times q1 minus q2 into this double inequality, we obtain negative b is less than b times q1 minus q2 is less than b. Now, since b is positive, then we can divide all three sides of this inequality by b to obtain negative 1 less than q1 minus q2 is less than 1. And since b is positive, it preserves the sense of the inequalities. Now, since q1 and q2 are integers, then q1 minus q2 is also an integer. Since the only integer strictly between negative 1 and 1 is 0, this inequality implies that q1 minus q2 is equal to 0, and hence q1 is equal to q2. And this implies r2 minus r1, which we said earlier was b times q1 minus q2, will be 0. And hence r1 is equal to r2. So we've shown that q1 is equal to q2 and r1 is equal to r2, and thus the quotient q and remainder r are unique. And this completes the uniqueness part of the proof, which completes the proof of the theorem. Now, there are two basic approaches to proving some quantity or mathematical object is unique. The first approach, which we used in the above proof, is to suppose that there are two such objects, and then to show that the two objects are really the same or equal to one another. And that's what we did there. We supposed that we had q1 and q2 and r1 and r2, and then we showed that q1 is actually equal to q2, and r1 is actually equal to r2. Now, the second approach is to use a proof by contradiction. We start by supposing that there are two different objects, and then derive a contradiction. And supposing the two objects are different or not equal provides an additional hypothesis that is sometimes useful in the proof. Now, the following example shows how we can apply the division algorithm to prove properties of integers. So for this example, we want to prove for any integer n, if n is odd, then there exists an integer k such that n squared is equal to 8k plus 1. And the statement can be written in symbolic form as, for all n in z, if n is odd, then there exists a k in z such that n squared is equal to 8k plus 1. To prove this, we'll suppose n is an arbitrary integer. We want to suppose the hypothesis that n is odd. We then need to show the conclusion there exists a k in z such that n squared is equal to 8k plus 1. Now, to prove this result, we want to use the division algorithm to introduce cases. It may not be clear why we need to use the division algorithm at the beginning of the proof, but as we go through the proof, you'll see how it's helpful. So using the divisor b is equal to 4, the division algorithm implies there exist unique integers q and r such that n is equal to 4q plus r and 0 is less than or equal to r is less than 4. So what we're doing is we're starting with our arbitrary integer n, and we're dividing it with a divisor of 4. And the division algorithm tells us there's a quotient q and a remainder r satisfying these two conditions. Now, since 0 is less than or equal to r is strictly less than 4, then the remainder r has four possibilities. It can be 0, 1, 2, or 3. So we can restate our conclusion as saying there exists a unique integer q such that n is equal to 4q, or 4q plus 0, or n is 4q plus 1, or n is 4q plus 2, or n is 4q plus 3. And this gives us 4 cases. However, our original hypothesis said that n is odd, and since n is odd, then only the second and fourth possibilities can occur. The first possibility, n is equal to 4q, would tell us that n is even, and the third possibility, n is 4q plus 2, would also tell us that n is even. And so since n is odd, we only have to look at the second and fourth possibilities. So we can conclude there exists an integer q such that n is 4q plus 1, or n is 4q plus 3. And this gives us just 2 cases we need to consider. So case 1, let's suppose there exists an integer q such that n is equal to 4q plus 1. We need to show there exists an integer k such that n squared is equal to 8k plus 1. That's our conclusion. So we need to prove existence of an integer k. So there's 2 parts to an existence proof. We need to find a k, and then we need to verify that k satisfies our conditions, namely our domain, k must be an integer, and our propositional function, which is, in parentheses, n squared is equal to 8k plus 1. So now to find a k, we're going to use our hypothesis in this case. We can say that since n is equal to 4q plus 1, then n squared will be 4q plus 1 squared, which is 16q squared plus 8q plus 1. And comparing this with our propositional function, we want something that looks like n squared is equal to 8k plus 1. So what we're going to do is we're going to factor an 8 out of the first 2 terms on the right. So n squared is 8 times the quantity 2q squared plus q plus 1. Now this looks just like 8k plus 1, where k is equal to 2q squared plus q. So that's what we'll choose for k. So we've now found our k, and we need to verify that it satisfies our 2 conditions. So first is our domain. Now since q is an integer, and the set of integers z is closed under multiplication and addition, then we know that k equal 2q squared plus q will also be an integer. So we've satisfied our domain. And then for the propositional function, this holds since n squared is equal to 8 times the quantity 2q squared plus q plus 1, which is 8k plus 1. So this proves the existential statement, so it proves case 1. Now for case 2, we're going to suppose there exists an integer q such that n is equal to 4q plus 3. And we again need to show the same conclusion, that there exists an integer k such that n squared is equal to 8k plus 1. So we again need to find a k and verify that k satisfies our domain and our propositional function. In this case, since n is equal to 4q plus 3, then n squared will be 4q plus 3 quantity squared, which is 16q squared plus 24q plus 9. And we want this to look like 8k plus 1. And so what we're going to do is we're going to start by breaking up the 9 and rewrite it as 8 plus 1. And now that gets us the plus 1 part of our propositional function. And then looking at our first 3 terms on the right there, you can see there's a common factor of 8. So this will be 8 times the quantity 2q squared plus 3q plus 1 plus 1. And now this looks like our propositional function, so we want to choose k to be the quantity in parentheses 2q squared plus 3q plus 1. So we've now found our k. We can go to the verification part, and since q is in z and z is closed under multiplication and addition, then k equal 2q squared plus 3q plus 1 is an integer. And the propositional function holds since n squared is equal to 8 times the quantity 2q squared plus 3q plus 1, which is 8k plus 1. So this proves the existential statement, so proves case 2. And since we've proved both cases, then our result holds. Now, suppose we had tried to prove the conclusion without first applying the division algorithm. we need to show for our conclusion there exists an integer k such that n squared is equal to 8k plus 1. The hypothesis that n is odd implies that there exists an integer t such that n is equal to 2t plus 1. Then n squared would be 2t plus 1 quantity squared, which is 4t squared plus 4t plus 1. Now, since this doesn't have the required form, n squared is equal to 8k plus 1 for some integer k, it's not clear how to proceed from this point. However, by first applying the division algorithm, we obtain n written as n is equal to 4q plus 1 or n is equal to 4q plus 3, and in each of these cases we are able to show that n squared has the required form.